This is a shark at max speed, this is the Aquaman, and this is me realizing how slow I am underwater. That's why over the last couple of months we've been finalizing the most overpowered human propulsion system. A 25 horsepower vehicle with the only purpose of measuring the fastest underwater speed we can. We started building it in the last video, however we didn't succeed at making it faster than a great white shark. I know, seems like a tough opponent, but since then we've learned a lot, so in this video we'll fix our issues and then improve our design step by step, facing unconventional setbacks until we finally see what it takes to be faster than a shark. And also whether us humans were even ever supposed to go that fast.
Oh shit! I broken my ears. Like I wasn't meant to go that fast underwater. Ow.
To get you up to speed, the overall principle is dead simple. We hold on to a tube with a lot of batteries, which power two large electrical boat motors on each side, and they make us go forward. There's a bunch of safety features, and one of them is the fact that we can change speed modes from 1 to 4. Now the issue is, the motors would stop working on the highest speed mode, mode 4. We would accelerate for a split second, and then at least one motor would stop turning immediately. It was incredibly frustrating because we didn't know why it happened. After we came back from the pool, we quickly realized that it could just be caused by the software on these motor speed controllers. And after a bit of adjusting, it turned out true. Speed mode 4 was suddenly kind of unlocked, so we tested it again in the pool.
Zoom out. Alright.
Here is the fastest run. However, after carefully calculating the speed frame by frame, we could only achieve 11.3 km per hour. That's much faster than the fastest human swimmer, but not enough. Our grand goal we set for ourselves is over 2 times that, 25.2. By the way, according to all of our credible sources, sharks are not faster than that, and Wikipedia is just wrong. Anyway, 11.3 is our baseline for what's to come next. We figured that the reason it's not as fast as we need relates to the topic of hydrodynamics. Hydrodynamics is a concept which explains why some fish are so extremely thin and streamlined. I mean, look at that. So we made a so-called hydrodynamic analysis of our vehicle. Now all of these lines and colors can tell us a much more insightful story. They reveal exactly where the flow separates, creating high and low pressure zones. We identified 4 parts that slow us down by creating unnecessary drag. First, these handles, then the motor mounts and motor hubs. They are all sticking out of the main tube and have flat surfaces which act as a brake.
It's like instead of a car, it's a truck, because it has a flat front and also a flat end, so there's a high pressure here and very low pressure here.
But surprisingly, it's not that simple, because the 4th part makes more difference than all of the previous ones combined, and it is the human itself, holding onto the handles. To understand it better, here's what's happening. By the way, setting this human in a correct position is harder than you think, but this position is good enough. So, there's 100 kilograms of the thrust force. At a speed similar to a shark, these 3 features create 53 kilograms of drag. The human creates 78 kilos. So, how to eliminate unnecessary drag? We can put this very unhelpful human, that is me or Peter, in line with the vehicle so that we become even more integrated with the overall shape. And as a result, less area will be exposed to the flow of the water. As you can see, from the front the shape is much smaller now. Excellent, but after we figured out the ideal position, we had to do a quick redesign to accommodate this new position.
Unfortunately, as pretty as this is, we need to tear it apart, so...
Let's tear it apart.
The handles go toward the back, and by the way, they also should be moved a bit down, because from our experience, their current position would pitch us upwards. And with these fairings, they are much more hydrodynamic. Now, the motors need to be moved toward the front, and we can also improve hydrodynamics by making it smaller. If you look at the cross-section, the most hydrodynamic shape is teardrop-like. The thinner it is, the better, but at some point it will be too weak if printed out of plastic.
What?
That's why, to make it stronger, we made it even thinner and decided to print it out of metal. It's not often that you get to see metal 3D printed parts, so it's always really exciting when we get them from JLC 3DP.
It's so cold.
Wow. But this is like real steel. It's like no bullshit.
On top of the fact that these are metal, it's 316 stainless steel, so it's good to use underwater. To order these from JLC, we just upload the 3D model file and get an instant quote. Here's the price for one mount, which is honestly quite alright considering how expensive all of the metal 3D printing equipment is. Look how much thinner these new mounts are. The shape is also of course much smarter now. If you don't have a 3D printer or just want to get parts from really cool materials like even titanium or transparent resin, go to JLC 3DP to get a coupon code for your first order. Link in the description. After all of the hydrodynamic improvements, we checked our results in the hydrodynamic simulation. Wouter, who's the founder and CEO of the company that made this program, even explained to us the simulation results in detail, and thanks to him we were able to come up with this improvement.
And in between the hands you have like the water intake.
Thanks a lot, Wouter. This program is actually a website called AirShaper, and you can also use it. I linked it in the description. And look at these results. The drag force decreased over 2 times. So we went to test it again. Okay, it's getting dangerous at this point because it's very fast, but it still wasn't as fast as we wanted. We achieved 13 kilometers per hour, which is 3.7 meters per second. We improved by only about 2 kilometers per hour. We were honestly kind of stumped at this point and couldn't figure out what's the deal. According to our initial 100 kg thrust test and then the hydrodynamic analysis for drag, we should be able to go much faster, but we can't. We're missing something. We analyzed the body position from the side, and actually Peter wasn't in an ideal one, which we put into the simulation. So we thought that maybe there is a chance that it's just because of that, but we weren't sure. As you can see here, we also lost the front dome in an accident, which for sure made it less hydrodynamic, but we doubted if it makes that big of a difference. We had to wait a week before the next test, so being completely at loss, we tried to replicate our initial thrust test, even though we for sure didn't think we could see any difference.
And I'll be measuring the thrust with one motor in the water.
As you may remember from the previous video, using this rig right here, we determined that the maximum thrust for one motor is 50 kilograms, making it a total of 100 for 2 motors. Again, in case you don't remember, this is the force which pulls us forward. So we should see 50 kilograms on here again.
Ready?
I guess we didn't foresee this. We got a maximum of barely 30 kilograms.
If it's really 30 kilograms, that means we can probably make it much more powerful, much faster.
Honestly, that's kind of weird that this happens.
So I know it sounds weird, but it's actually good news. The motor, in order to spin, needs to get electrical pulses from some sort of a device, a brain of the motor, which tells it how exactly to spin. It's called an ESC, electronic speed controller. Essentially, we were stupid enough to use these electronic speed controllers in the pool, even though earlier we tested the maximum thrust with this one. The new ones were supposed to be just better, but we didn't even bother checking. And there was our downfall. The new electronic speed controllers are called VESC, and they are so intelligent that they decide to limit our power, just so that they don't explode. So we put on the initial cheaper speed controller, which doesn't have any limits, which is quite awesome.
Oh, they broke. Oh, wow. So, yeah, it has a little bit more thrust.
After a couple more tests, we even got 60 kilograms.
3, 2, 1.
Now look at this. If earlier we achieved 13 kilometers per hour using 30 kilograms, what is the speed we could achieve using 60 kilograms?
Okay, I think we're gonna be pretty fast. What do you think?
I think we're gonna beat the out of sharks.
Yeah.
I think the sharks are gonna be swimming away from us.
But on the other hand, this cheap ESC with no limits has one problem.
Oh no. Oh shit! Oh no, that was the ESC? Oh no!
Yeah, it worked overtime for sure. So in short, we had to buy even more expensive ESCs, wait another week, and after replacing it, it finally worked. We still got 60 kilograms, but it won't burn.
Oh no. Wait.
You're laughing at my suffering.
And by the way, it's 120 in total, of course. We were almost ready to test the new maximum speed. But looking back again at the position Peter was swimming in, with even more thrust it wouldn't have looked pretty. Because he's clearly not fully in control. And I don't know if you've noticed, but it stems from the fact that the vehicle is for some reason on its side. Why is that? You might think that it's because it's perhaps heavier on one side, but no. You see, it's caused entirely by the fact that we used identical propellers on each side, and so both motors had to turn in the same direction. Now, if the motors spin the water mass this way, the entire vehicle is pushed in the opposite spin. It is a very well-known principle which we knew about beforehand, but the issue was that the motors come with only one type of propeller. There are no mirrored versions. If we had a mirrored one, the motors would spin in the opposite directions, and the vehicle would no longer rotate by itself. And then Peter wouldn't need to spread his legs like that, trying to counteract the spin. It also slows him down slightly. But since nobody makes mirrored propellers like these, the only way to get it was to make it ourselves. We scanned the propeller by doing photogrammetry, so just a ton of photos, which then made this rough model. Here's a polished version, and now it's trivial to mirror it. Then, thankfully, we recently got this printer, just for the occasion. We did 3D print propellers before, but we always had an issue of the print layers making it very unsmooth. And this is a resin printer called Form 4 by Formlabs, and the layers here are extremely thin, so much smoother. We picked this Tough 2000 resin, and I hope it's tough enough. Because it's resin, it also means that we need to do a little additional post-processing in alcohol and then in UV light. This is the result. Exactly what we wanted. It also has a slot for a star at the bottom, which serves as a mounting point. We assembled the vehicle back together, and finally it was time for another swim test. But this time, for this special occasion, we want a big water reservoir with very clean water. That's why we traveled 16 hours over 1600 kilometers to Croatia.
Perfect.
Well, it's so see-through. So clear.
See-through.
It's see-through.
We wanted to do this for a long while, because now we can roam freely wherever we like.
This is mode 4?
Yeah, it's mode 4.
Okay, nice. Oh shit! Holy shit!
Oh my god!
Holy shit!
This wants to kill me. Feels like going in a jet. Ah!
Let's try the max speed, straight to mode 4.
What? What the heck?
But this isn't even top speed, because Peter can't hold the throttle for long enough.
I broken my ears. I got like water in them and they hurt. Like I wasn't meant to go that fast underwater. But this was so scary. And I'm scared to like go for more than 1 second. It just feels like I don't know, like a car hit me or something.
Aside from the fact that it's tough for Peter to swim at that speed, the worst part is that the propeller broke on one of these runs.
Oh no.
We don't really know why, but I guess from the speed. So in the moment we thought of buying some sort of over-ear protection, but that would need to wait for now. The next day we replaced the propeller, but right when it was time for the second dip, another thing broke.
Really?
At this point I call it bad luck, because it was another ESC, the more expensive one, which worked during testing. We spent the entire day trying to fix it on the beach, unsuccessfully. On the third day in Croatia, we managed to record some of these cool shots, but all of them at relatively low speed. But then, quite randomly, water got inside of the main tube with all the batteries, and I had to rescue the vehicle from the sea bottom. That was a series of unfortunate events.
This is the moment we have decided to give up.
Despite saying that, we decided to give it one more shot. So we had to come back and hopefully for the last time fix everything, buy new components, wait a week, reassemble, and go to the pool.
If this doesn't work, I'm fine with getting eaten by a shark.
Hopefully the pool is big enough so we don't die. Also, we could test the theory for ear protection using this water polo helmet.
I look like a clown.
Maybe that will allow humans to achieve larger speeds.
But my ears don't hurt, you know?
Ears don't hurt?
Yeah, I mean they're much better. I think I could go even faster now without like ear fracture. Ears broken.
Yeah.
And this is the fastest run we got. And here's a comparison to a swimmer, also Peter. Right after we came back and calculated the speed frame by frame. The final speed? 18 kilometers per hour. Now listen, I know we didn't beat a shark at 25 kilometers per hour, but we realized that at this point going faster is not an activity we want to take part in, mainly because of this. We've recently started creating DIY kits for an underwater project you can build at your home, even as a beginner. It's an underwater drone called CPS-3 and we'll release the first small batch at the beginning of February, so sign up to our newsletter by clicking this button to get notified immediately when it becomes available. The link is in the description. For now, we are done with this vehicle, but here's our another project which you might enjoy watching. Thanks!